Hey fellas, welcome back. I know I'm sitting kind of alarmingly close to the camera today, but I'm going to kind of try this one out. Yes, I have bad skin. Welcome to the party. I'm a coder. What else is new? So first of all, quick announcement. Thanks everyone for 7,000 subscribers. I really appreciate that. And yeah, I'm eternally grateful to all of you, especially those of you who have been here since even like before I collaborated with Gorov or whatever and got a few thousand people. Yeah, again, I'm making these videos to help people mostly, and the subscriber count is not really what I'm optimizing for at the end of the day, but to me it indicates that people are gaining some usefulness out of this channel, and that makes me a happy guy. I always want to try and help, and I think I'm doing that so far, so that makes me very happy. Additionally, the more subscribers I get, I can stick it to this one TikTok girl that I went out on a date with, and she was not into it. So let's move on from that and get into some content for today. All right, we're back in action. I've got the iPad in front of me, so let's get started. So today I am going to be talking about another race condition, and I do not mean Israel-Palestine. I mean repeatable read, which is also known as read skew. So basically, the way I'm going to go ahead and talk about this is by doing the following with an example. So let's imagine I have a table that shows all the bank accounts of the Kardashians. I know there are 8 names on here. There might be more than that. I'm sorry I even know 8, but don't judge me, whatever. So the predicate of this table, let's imagine that we know the balances must add up to $1 million. They at one point did add up to $1 million, and I'm going to make the arbitrary constraint that basically they can only exchange balances with each other. So there's always going to be $1 million of value in this table. Okay, so we have basically all the Kardashians listed below and their respective balances. I got pretty lazy finding 2 more names, hence why Scott has 300K. So let's imagine that I'm doing some kind of housekeeping work for the family. I'm going through the database and telling everyone how much money they have in their bank account. So that's going to require me to read every single row of the database and then return all of those values. So it's going to start something like this. I'm going to read Caitlin, I'm going to read Kylie, I'm going to read Kendall, I'm going to read Chloe, I'm going to read Courtney, and then right before I read Chris, Caitlin decides that she needs some more plastic surgery. So all of a sudden, Chris, the mother of the family, is going to send Caitlin her $100,000. So now Caitlin actually has 200K. And Chris has $0. So basically the invariant of the table still holds, right? All these values do still add up to $1 million. But we had already read that Caitlin's value was 100K. And now when we finally get to Chris, we are going to read that her value is 0, because this write has just executed in the middle of our massive read, right? Our writes don't actually block reads, and we're still reading committed data this entire time, so there's no issues here. But now, when we add up all of these balances, we're actually going to be minus 100,000, because we didn't account for the fact that Caitlin is going to be getting another 100,000 midway through the read. So that is basically the idea of read skew. We have this table, it has some sort of invariant, and ultimately due to a write in the middle of some massive read, possibly due to an analytical query, the invariant no longer holds. We want to be able to see the database in a consistent state, and basically because we were doing this long read and there were writes interjecting it, we weren't able to do so. So let's think about ways that we can fix this. And the way that I'm going to propose starts with our friend, the write-ahead log. So let's go ahead and scroll down. So as we know, every write that goes into a database is going into our write-ahead log. That's really useful for both durability and atomicity. And so for the write-ahead log, it's just one list on disk and all the writes are sequential. So what this allows us to do is actually go ahead and order transactions. So as you can see, if we're making sure that writes and reads block each other, they don't necessarily have to, so I can take this one out. But we have a write at T1, we've got a write at T2, we've got a write at T4, and basically whatever hits the write-ahead log first, we can assign a monotonically increasing sequence number. Monotonically increasing just means that it's going up by 1 every single time, but it's not a big deal. And same goes for all of these other lines right here that we're adding in the future. They're going to get sequence numbers as well. So we've now basically given all of our transactions a number. And for a given transaction, let's say we want to be able to see a consistent snapshot of the database at the time that that transaction was written. So let's see an exercise of how we can actually do this. So let's imagine we have a bunch of writes to our database, which again has the account balances of a bunch of Kardashians, and we want to basically see the database snapshot at T15. Well, the way that I'm basically going to propose that we do this is every single time that a value gets overwritten, instead of just deleting that value, what you do is store all of the values with the transaction number that wrote them, and then keep all of those values. So as you can see, transaction 1 basically said that Caitlin's bank account balance was 100K. On transaction 6, it was overridden to be 300K, and on transaction 12, it was overridden to be 200K. The point is here, you don't have to actually write a value for every single one of the transactions, but only the transactions that modify the rows themselves. So these are going to be relatively sparse. It's not going to take up a ton of extra storage in theory. Okay, so let's imagine we want to basically see what the database was looking like at T15, right? So whenever transaction 15 was written. So right off the bat, we know that something like this right here, which was written in transaction 17, is invalid. And the same goes for this write that was done by transaction 22. So to really find what we care about from transaction 15, I'm going to draw this line that basically cuts out all the writes after transaction 15. And then for all of the rows, we're going to take basically the most recent value that was before 15. So in the case of Caitlin, that's the write that was done at transaction 12. So she has $200,000. In the case of Kendall, it was the write at transaction 15, so she has $1 million. In the case of Chris, that key was only written at transaction 22 in the first place. So at transaction 15, Chris doesn't even exist. There's no row for Chris in the database. And then finally, for Lamar, it was only written once at transaction 3, and there's going to be 100K. So basically, again, the point is you don't delete these old values, but rather you store them. And so for these big reads that we might have that take a long time to execute, we don't have to risk seeing the database at some inconsistent state, but rather we can use a database snapshot. And that right there is the premise behind snapshot isolation. So guys, I hope you enjoyed this video. Relatively short, but hopefully simple. My point of this new series is to make sure to really hone down on topics and not brush over them like I at times did in my previous series. Snapshot isolation I probably covered in all of 30 seconds in my previous series, and while that's good for some people, for others, it is, good to make sure to really cover every single edge case and make sure that you really understand it. So anyways, guys, have a great night. Wishing you all the best, and thanks again for all the love.